Hey there. Today we're going to be doing jump game 1. So, well, I did jump game 2 just now, but we'll also do jump game 1. This is a bit more simple than 2, if you somehow done 2 and not 1. But basically we're just given an array nums. We're positioned at the first index, and for each element in the array, or each element in the array represents your max jump length. Return true if you can reach the last index or false otherwise. I guess one caveat for this question is that this 2 here represents our max jump, so we can actually just jump one as well, one time as well. So yeah, that kind of confused me at the start because I was just thinking of this sort of like a graph, a directed graph where it's from here we can go to index 2, and here we can only go to index 4. But actually no, this is the maximum jump we can do. So we can either jump once here or twice here, right? And then here we can jump once, twice, or 3 times. The central point to understand here is that we're going to use a greedy approach for this problem. Exactly why is because we want to just maximize the current reach or the current jump we can do to get to the last index. I'm not sure if that's intuitive for you or not, but basically you can just think of the problem as having, you can think of the problem in a reversed notion. Basically this is the target we're going to do, right? And where can we get to? Or how do we get to the target, right? We have to jump from the previous index. So the new target is here basically. And then how do we get to here? We have to jump from the previous index, right? And so the problem becomes, how do we reach the, how do we get to the current last element and then iterating back from it backwards into the first element? Obviously, all we want to do is just try and reach it as far as possible so that we can try and reach this goal, right? And essentially what we're doing here is we're just checking for each index. Can you reach this? Can you reach this? Can you reach this? But we're doing it from the start. So the best way to do that from the start is simply to check through the maximum of the range to check if we can reach that, essentially, right? So the approach here is just we keep track of the maximum index. So here the maximum index we can reach is 1. From here the maximum index we can reach is 3, so 1, 2, 3 here. And we notice that this is the end, so we know that there is a solution for this, right? That's sort of the approach, at least. Here we know that the maximum index we can reach is, so 1, 2, 3 here, right? The maximum we can reach from this index is also 0. The maximum we can reach from this index is also 0, and then 0 we can't really do anything. So we notice here that the current, when we're iterating the last element, we notice that our current reach is 3, but we're at index 4, right? So notice here there's a discrepancy. We're going to use this as the invariant to determine that it's false, basically, that there is no solution to the end. Here, obviously, we know that this is 1 plus 3, which is 4. So this is approachable. Once we get to the last index, we have determined that this is the maximum reach we can get from each index. And then it's a check, because 4 is not less than 4, basically. It's not less than 4, right? And that's just the logic of our algorithm, essentially. Now, to code it up, we're just going to use a maximum reach, or maximum jump. We can set that to 0. And for I in range len nums, or sorry, the maximum jump should be the first element, actually. Because we're just going to check through the next few elements after. So for I in range 1, len nums, we want to check the max jump, which is going to be equal to the max of the current max jump and I plus nums I. Since obviously, yeah, this part here, right? I is 1, and jump is 3, so it can reach index 4. And we want to check here also the invariant. Before we even try to attempt to jump, what if there's 0 here, right? What if there's element 0? We can't jump anywhere, so we already have to terminate this, right? So we want to check when our reach is 0, and we want to get to index of 1. When we're iterating through index 1, we know it's not possible, right? So basically we have to keep track of, we have to keep checking for each index. Let's say there's 1 here. We have to keep checking for each index, can this element even be reached? And that's how we check the solution, right? Can this element be reached? Yes, because we have maintained that the reach is 4, so we can get to 4. We can get to the 4th index. So we want to check for this element here, is there a reach that we've previously checked to that can even get to this element? And that's the intuition of why we're going to check for the reach at the start of the list, actually, or at the start of the loop, basically. And so if our I, which is the current element we're in, if our max jump is less than I, so here in this case, our max jump or our max reach is 0, and our index is 1, right? So here 0 is less than 1, we just default to returning false, basically. And so here, return false. And if we went through the entire array and we found that each element, each index can be reached, then we return true. And that's basically the entire algorithm. It's pretty simple, although the greedy intuition of doing this problem is a bit odd, you can say, unless you've already encountered the problem before. And this solution is O of n time as well, because we're only iterating through the array once. We're not doing any special operations. We're even not really using anything else, so the space complexity is also O of 1. The space complexity is O of 1. Write that down. S is O of 1. Time is O of n for this algorithm. Yep, that's it. Thank you for watching.